Good morning, students. Yesterday we have discussed the terminologies and concepts of geometry. Also, we have discussed the definitions of solid geometrical concepts, then the definition of a point, then definition of a line, the definition of a plane geometry, surface geometry. Yes. So today we are going to learn about the equation of a plane. Before that, we have see here the definitions which we use later. So the first definition is here: direction cosines of a line. If alpha, beta, gamma be the angles which any line makes with positive direction of a axis, then cos alpha, cos beta and cos gamma are called the direction cosines of the given line and are denoted by the letters small l, small m and small n respectively. Yes. So the next definition is direction ratios, the set of three numbers which are proportional to the actual direction cosine are sufficient to specify the reaction of a line. Such numbers are called the direction ratios. So thus, if ABC be the direction ratios of a line, then its direction cosines are given by this one, plus or minus a upon root of summation of a square, plus or minus b upon root of summation of a square, and plus or minus c upon root of summation a square. Next definition is projection of a point on a line. I think you have understand the definition of a direction cosine of a line and direction ratios. So see here the next definition: projection of a point on a line. The foot of the perpendicular P from a given point A on a given straight line BC is called the orthogonal projection, or it is also called as a simple projection, yes, of the point on the line, and is the same point where the plane through the given point and perpendicular to the given line meets that line. Yes. So we use these definitions in the succeeding theorems. Now look at here the main theorem. So see here. So this is our first theorem on the plane. So what is the statement or the result of this theorem? Every equation of first degree in x, y, z always represent a plane. So I repeat again, every equation of first degree in the variable x, y and z represent the equation of a plane. So how? So see here the proof of this one. The general equation of a plane of first degree in x, y and z is given by ax plus by plus cz plus d is equals to 0. So this is the equation, and it is a general equation of a plane in first degree in a variables x, y and z. So we have to show this equation is a general equation of a plane. So you can consider here, or you can assume P x1 y1 z1 and P x2 y2 z2. These are the 2 points on the locus represented by the equation number 2.1. Then we have, it means that if these 2 points are, we can assume these are the locus of points represented by this general equation. It means it satisfies the general equation of a plane. So see here, you can put this x1 y1 z1 in equation number 2.1. So we get ax1 plus by1 plus cz1 plus d is equals to 0. Similarly, you can put the second point P, or we can write it as a Q. x2 y2 z2, we get ax2 plus by2 plus cz2 plus d is equals to 0. After that, you know how to solve the system of algebraic equation, because such a type of system of algebraic equation you can study it in a 10th, 11th and 12th standard. Yes. So just you have to solve this one and find the coordinates or find the variables x1, y1 and z1. Yes. So for that you can multiply the equation number 2.3 by some arbitrary constant k, then we get, so you can multiply here to k, so it is akx2 plus bky2 plus ckz2 plus dk is equals to 0. So here you can multiply this k to each and every term of equation number 2.3. Now adding the equation 2.2 and 2.4, then we obtain. So here you have to add this one and this one. We get a is constant here, both here is common, x1, x2, kx2. So that's why it is x1 plus ax2 plus b into y1 plus ky2 plus c into z plus k z2 plus d in bracket 1 plus k is equals to 0. So thus for k is different from -1, the above equation becomes, means this one, look at here, above equation becomes a in bracket x1 plus ax2 divided by 1 plus k plus b in bracket y1 plus ky2 divided by 1 plus k plus c in bracket z1 plus kz2 divided by 1 plus k plus d is equals to 0. Call this as equation number 2.5. What we do here, just you can divide the coefficient of this one, this term 1 plus k, to each and every term of this equation, we get this one. Yes. Now the equation 2.5 and his coordinates are, if you observe the equation number 2.5, the coordinates are this bracket one, this one and this one, and you can write here. These are the coordinates, and these are satisfied the equation number 2.1, means our general equation, and which divides the line joining the points P and Q, yes, into the ratio. And what is that ratio? Ks to 1. So if you observe here this one, this equation and this equation as the ratio of these points P and Q as Ks to 1. So also it lies on the locus of the general equation 2.1. Hence all the points lie on the line PQ also lies on the locus of that 2.1. Locus means it is the position of that point 2.1. Thus we conclude that every point on the straight line joining any two arbitrary points on the locus also lie on the same locus. Yes, and hence the equation 2.1 represent a plane. Yes, so the equation ax plus by plus cz plus d is equals to 0. This equation represent a plane, and that's why we can write here every equation of first degree in x, y, z represent a plane. So I think all of you understand very well this theorem. I repeat again, the statement of this theorem is every equation of first degree in x, y, z represent a plane. Yes. Now let us see here the next one, normal form of the equation of a plane. Just a minute, I will show you here the next, I think it is here or not, just we check it. Okay. So this is the normal form of the equation of a plane. So we have to find here the normal form of the equation of a plane. So see here the result, it is a theorem, and the statement of this theorem is we have to show or we have to prove Lx plus my plus nz. Now you know what is L, M and N. So L, M, N are what are those elements? Are direction cosines. Yes. So this is equals to small p is the equation of plane where small p the length of the normal from the origin to it and L, M, N are the direction cosines of that normal. So we have to show here Lx plus My plus Nz is equals to P. This equation is of a plane, yes, and it is a normal of that by using the direction cosines L, M and N. So look at here the figure, this one. If you look this figure here, it is x axis, y axis and z axis. Yes, so this is the point P. So let us see here the description of this figure. Let this K, this one, this K be the foot of the perpendicular from the origin. Means K is the foot of the perpendicular from the origin to the plane. Yes, so this one is the plane. Yes. Let OK be the normal from O to the given plane. Are you understand? OK, that segment OK, it is the foot of the perpendicular from origin, and that OK is normal to the from this point O to the plane. Then you know OK is equals to P and L, M, N are its direction cosines. So take now any point P, capital P, whose coordinates are x, y and z on the plane. Now PK lies in the plane which is a perpendicular to OK. Are you understand? You can take PK lies on the plane which is perpendicular to OK, and therefore the projection of OP on OK, it is equals to small p. Also the projection of the line OP joining the points this O whose coordinates are 0, 0, 0 and the point P whose coordinates are x, y and z on the line OK whose direction cosines are L, M, N is given by this one. So the direction cosines of these 2 points O and P is given here. L in bracket x minus 0 plus M in bracket y minus 0 plus N in bracket z minus 0 is equals to what we get? It is Lx plus My plus Nz. Yes. Hence Lx plus My plus Nz is equals to P. What is this? So this is the equation is satisfied by the coordinates of any point P, x, y, z on the given plane, represent the plane and is known as the normal form of the equation of a plane. So what is the normal form of equation of a plane? We have discussed here the proof, but you can remember the normal form of equation of a plane is Lx plus Lx plus My plus Nz is equals to small p. Are you understand? What are L, M, N are direction cosines. Yes. Now we will discuss here the next theorem. So see. So it is transformation of a general equation of plane to the normal form. Yes, we have to find the transformation of general equation of plane to normal form. So let us consider, you know, it is ax plus by plus cz plus d is equals to 0. It is the general equation of plane. Yes, and let Lx plus My plus Nz is equals to P is the normal form of that plane. Yes, it is normal form of the equation number 1. You can denote this is the equation number 1 and this one is 2. Since 1 and 2 are the same, why? If you observe, the Lx here is ax plus by, here is My, here is cz, here is Lz, and you can take this P on left hand side, we get minus P, and if you compare these two equations, we get the coefficient is 1 by A is equals to M by B is equals to N by C is equals to minus P by D. Yes, and this is implies root of L square plus M square plus N square divided by root of A square plus B square plus C square. So which is equals to plus or minus, you know it is the root of L square plus M square plus N square. This is the direction cosines, and that's why it is equals to 1. Yes, and that's why we write it is 1 divided by root of A square plus B square plus C square. Or we can write it is L by A is equals to M by B is equals to N by C is equals to plus or minus 1 by R. Yes, and what is R? R is the root of A square plus B square plus C square. So by using this computation, we have L is the direction cosine, which is equals to plus or minus A by R, M is equals to plus or minus B by R, and N is equals to plus or minus C by R, and P is equals to plus or minus D by R. So from the equation number 2, so what is the equation number 2? It is a normal form of the equation of a plane. That equation of the general equation of a plane is given by this one plus or minus A by capital R x plus or minus B by R y plus or minus C by R is equals to plus or minus D by R. Yes, where R is the root of A square plus B square plus C square. So since P is always positive, then the sign in is so chosen that P is plus or minus D by R is always positive. So you know this is the remark on the normal form of equation number 1, and this is equals to D is a minus or negative. The normal form of 1 is given by this one. Yes, so we can see. So from the equation number 3 means what? This one. So from this equation, what we get? Look at here. From this equation 3, we see that the direction cosines LMN, yes, of the normal to the plane are proportional to A, B, C. It means the coefficient of x, y, z. Thus, the direction ratios of the normal to the plane ax plus by plus cz plus d is equals to 0 are A, B and C. For example, the direction ratios of the normal to the plane 6x plus 2y minus 3z is equals to 11r. So if you compare the equation 6x plus 2y minus 3z is equals to 11 with ax plus by plus cz plus d is equals to 0, we get the direction ratio is 6, 2 and minus 3. Just you have to compare that equation with general equation. Yes, and you know it is a square plus b square plus c square, and that's why it is 6 square plus 2 square plus minus 3 square, and it is equals to 7. And thus the direction cosines of the normals are 6 by 7, 2 by 7 and minus 3 by 7. Yes. So this is the example we have shown how to find the direction cosines and direction ratios. Yes. Look at here the next example. Show that the normal to the plane x plus 5y minus 3z plus 6 is equals to 0 and 2x plus 2y plus 4z is equals to, what is this, 1 are perpendicular to each other. That we have to show here. So look at here the next one, how to show this one. So the same example you can do at home. It is left as an exercise. If you face some difficulty to solve that example, you can comment on that our YouTube channel. Yes. So see here the next one is angle between two planes. We have to find the angle between the two planes. So the angle between two planes is equals to the angle between their normals. Yes. So consider the two planes. You know the general equation of plane is. So here the first plane is a1x plus b1y plus c1z plus d1 is equals to 0, and the second plane is a2x plus b2y plus c2z is equals to plus d2 is equals to 0. Call these two equations number are 2 and 3. So these two are the equation of a plane. We have to show here we have to find here the angle between these two planes, it means that we have to find the angle between their normals. So what we have to do here? First we have to find the normals of this one. Yes? So you know how to find the normals. So normal equation is Lx plus My plus Lz is equals to P. Means we have to find here the direction ratios of the normals to the plane 2 and 3. And these are, we can suppose it is A1, B1, C1 and A2, B2, C2 are the direction ratios of the normals of the equation number 2 and 3. So angle theta between the plane 2 and 3 is given by. So how to find the angle between two planes? It is the cos theta is equal to this formula, A1, A2 plus B1, B2 plus C1, C2 divided by root of A1 square plus B1 square plus C1 square into root of A2 square plus B2 square plus C2 square. So which is equals to theta. You can take this cos on right hand side, we get the cos inverse. And so theta is equals to cos inverse of that right hand side. Means this expression. And so it is the angle between the two planes. So this theta represent, this formula represent the angle between the two planes. Yes? Are you got my point? Yes? Now let us see here the remark on this one. If two planes, equation number 2 and 3 means A1x plus B1y plus C1z plus D1 is equals to 0 and A2x plus B2y plus C2z plus D2 is equals to 0. These two equations are perpendicular, then means it is in a right angle, then the cos theta is equals to cos 90 and you know cos 90 is 0 and thus from the equation number 4 the planes 2 and 3 are perpendicular. Yes? If A1, A2 plus B1, B2 plus C1, C2 is equals to 0. Means this equation means the direction cosine, both the planes are right angled, it means cos theta is 90 and that's why it is cos 90 is 0. Okay. And second remark is, if two planes 2 and 3 are parallel, then their normals are parallel. Therefore, the planes 1 and 3 are parallel if this A1 by A2, this ratio is equals to B1 by B2 and this ratio is equals to C1 by C2. So let us see here the one example on this one. Here we have to find the angle between these two planes. The first equation of a plane is 2x plus y plus z is equals to 5 and the second equation of a plane is x minus y plus 2z plus 3 is equals to 0. So just you have to find the angle between these two planes. So what we do? So first you can find the direction ratios. So direction ratios of the normal to the given planes, and what are those? So here the coefficient of x is 2, the coefficient of y is 1 and the coefficient of z is 1. Yes, if you compare this equation with your general equation of a plane, we get the direction ratios of this normal is 2, 1 and 1. Similarly, the direction ratios for this one is the coefficient of x is 1, the coefficient of y is minus 1 and the coefficient of z is 2. Yes, and that's why the direction ratios to the normal is given by here 1, minus 1 and 2. Yes, so therefore the angle theta between these two planes, it is given by the formula cos theta is equals to, you know, this one. Cos theta is equals to this one. Yes, so we use this one. Here in this example we get A1 A2 means 2 into 1 plus B1 B2 means 1 into minus 1 plus C1 C2 means 1 into 2 root of A square plus B square plus C square. It is root of 2 square plus 1 square plus 1 square into root of this A square plus B square. A1 A2 or A square plus B square plus C square. So these are 1 square plus minus 1 square plus 2 square. If we compute it, we get cos theta is equals to 1 by 2. So here cos of which angle is 1 by 2 means theta is pi by 3. Yes, and pi by 3 means it is a 60 degree angle. So cos of 60 is 1 by 2. Hence the angle between the two planes, this one and this one, we can find that it is theta is equals to pi by 3. I think all of you clear this example? All of you understand? Yes. So this is the next example, and it is left as an exercise for you. Find the angle between these two planes. I have given here the answer directly. It is a cos inverse of 4 by 21. You can solve this example at home. Yes. And the second is prove that these two planes are perpendicular. Okay. So today we will stop here. Tomorrow we will see the next concept. Thank you.